particles of mass are called photons. So each portion of the spectrum has associated photons. Now these photons are small packets of energy traveling at the speed of light, so they carry energy with them, just as a linebacker has mass and he's running down the street, right? There's energy associated with him, and if he slammed into somebody, that energy would be transferred to that individual. This photon can smack into stuff, and when it does, the energy from that photon is transferred into whatever molecule it bumps into. Photons can have different amounts of energy associated with them depending on which wavelength of light we're talking about. And the way the scale is drawn, the amount of energy is inverse to the wavelength. So shorter wavelengths, higher energy associated with the photons. Longer wavelengths equals less energy associated with the photons. So short to long wavelength is high to low energy. Okay? All right? Now, we could divide these into much smaller categories, right? The UV portion of the spectrum can be broken down into, so this is UV. This can be broken down into UVA, UVB, and UVC. The UVC gets blocked by the ozone layer. Most of B gets blocked, and then some of B and part of A get through the ozone layer. So your sunscreens and sunglasses often have a little thing that says blocks UVA and UVB. Right, the infrared can be broken up into different portions, et cetera, et cetera. The part of the spectrum now that we should concentrate on is the visible light portion of the spectrum. Okay, visible light. Very narrow, but we divide this portion of the spectrum up based again on wavelength, but in particular the color of the light that's associated with that wavelength. So we recognize 7 different colors here based on the wavelength and the associated color. In school you probably learned Roy G. Biv, right? Red, orange, yellow, green, blue, indigo, and violet. But notice on my image up here, because I'm going from short to long wavelength, violet light is of a shorter wavelength than red light, which is longer. It also means red light has less energy associated with it than violet light. Okay? All right, so I always joke that it's not Roy G. Biv, it's Viv G. Yor, until I picked up one of my kids' high school textbooks years ago, and indigo is gone from a lot of the textbooks, so now it's like Viv G. Yor, right, because they got rid of indigo. I don't know where indigo went. It's obviously still there, but now they're just talking about blue and violet with no indigo. They just bleed into each other. Okay? All right. Okay? All right, so as we start talking about light, let me introduce a few terms in here that are going to be important for us. The first term here is pigment. So a pigment is any molecule that interacts with light, and that interaction is in the form of absorption. So if I have my pigment molecule here and I hit it with some light, okay, let's hit it with visible light, because then we can talk about the colors, because we're all very familiar with light because our eyes are designed to see that light. So the light hits the pigment molecule. Now there are 3 fates to this light. The first possibility is that some wavelengths of light are actually absorbed. The second possibility is light is reflected. And And the third possibility is the light goes right through the pigment molecule without hitting anything, and we refer to this as transmitted light. Now, we can't tell transmitted light by looking at something, but we can tell something about the pigment molecule based on the light that's absorbed and reflected. So pigments are differentially absorbing and reflecting. So I have my fleece on here, right? You probably noticed it was a different color than the one I reviewed the exam with because it's actually a few days later. Shocker, I don't always do all the lectures all at once. So this is blue. There are pigment molecules in here that absorb and reflect different wavelengths of light. The wavelengths of visible light that are absorbed are all of the colors except blue. Blue light is being reflected back toward you. So the colors that we see are based on the light that's reflected back toward us. Okay? This appears blue because it reflects blue. The other wavelengths of light are not reflected. This whiteboard here appears white because all of the wavelengths of light have been reflected back, and our brain interprets the presence of all wavelengths of light as white. This little piece down here is black, so is this little band on my fleece. This particular pigment molecule absorbs all of the wavelengths of visible light and doesn't reflect any visible light. And because of the lack of any reflected visible light to your eye, your brain interprets this as the absence of light. It interprets it as black. So if there is no light, we interpret that as black. All visible light is interpreted as white, and any of the colors, red or white or purple or any of these colors, is interpreted based on what's being reflected back to your eye. Okay? And that's where I'm going to go ahead and break it for today, and then we'll pick up with photosynthesis next time.
Take care.